In the previous episode, we've been busy converting the program counter breadboards into a PCB and getting the PCB manufactured, assembled, and tested. With that out of the way, I think it's time to start working on the bare necessities that will give our processors the ability to perform basic arithmetic and to do some useful work in general. Be sure to like and subscribe if you want to see this project unfold. So let's say we want to add the numbers a and b. We will probably define an instruction called add. If our processor sees this instruction, it would go grab the values of a and b, do the operation, and then put the result back in a. But the question is, where is a and b even stored? As a first reflex, we might want to have operands a and b live in memory. After all, we're building a computer which generally has a lot of memory to store things. So getting operands from memory to do the computations seems pretty natural. To encode this in an instruction, we would somehow have to store the memory address of a and b in the instruction itself. So if we're building a computer with 8-bit addresses, we would need a few bits to say that this is an add instruction. Maybe 4 bits are enough for that. And then we'd need 8 bits each to store the address of the a and b operand. This leaves us with a total of 20 bits that we need per instruction. But 8-bit addresses really don't give us a lot to work with. That's just 256 bytes worth of memory that we can address. That's also the reason why we went for 16-bit addresses for the program counter and the program memory in previous episodes. So with these 16-bit addresses, our add instruction will still have 4 bits to indicate that it is an add, but then it will need 16 bits each for the addresses of a and b. That makes the instruction a total of 36 bits wide already. And it gets even worse the more address bits we have. In a 32 or 64-bit system, we need 32 and 64 bits each to store the address of a and b inside the instruction, which is going to require a total of 68 or 132 bits for the instruction, which is a lot of bits. To work around this problem of having to load data from memory for every single instruction and to store the addresses in the instruction, CPUs have registers to store the data that they are currently working on. As an example, let's assume we have 8 registers available, from R0 all the way up to R7. Instead of directly providing the addresses for operands a and b as part of the add operation, we first load a and b from memory into a register with a load operation, and then have the add operation work with those registers instead. And once the addition is done, we can store the result back to memory with a store instruction. At first glance, this looks like it's very inefficient, because we need 3 additional instructions just to do an addition. However, in practice, you are very likely to reuse the data that you loaded from memory, and you'll reuse it multiple times in general. The result of one instruction is very likely to be used in the following instructions instead of being written back to memory straight away. So the more registers the CPU has, the more intermediate results it can keep around and reuse before ever having to interact with the memory. On top of that, using registers in instructions makes the instructions a lot smaller. We have 8 registers, so we need just 3 bits to indicate from which register an operand comes from. In our add instruction, this means we still have the 4 bits to encode the add, but then just 3 bits for the a and 3 bits for the b operand, for a total of 10 bits to encode the entire instruction. This is a lot smaller than the 36, 68, or 132 bits that we needed to store the entire memory addresses directly in the instruction. Now, regardless how many address bits our CPU uses, the add instruction will always need just 10 bits. Only the load and store operations have to carry memory addresses, and only a single one at a time. Pretty much all commercial processors use registers to keep around the data that they're currently busy crunching. Over the years, the number of registers available to programmers has grown as the underlying silicon manufacturing technology has become more advanced, and we've been able to cram ever more stuff onto a small piece of semiconductor. In the early days, the 6502 processor, which among other things drove the very popular Apple II computer, had only 4 8-bit registers, and of those, only the A register was really used in computation. It provided one of the operands for the arithmetic instructions, while the second operand was loaded directly from memory. X and Y were indexing registers that could be used to modify the memory addresses accessed by load and store instructions, and SP was used as a stack pointer, which tracks the location of intermediate results kept in memory. Then a bit further down the road, the Z80 processor, which powered the Nintendo Game Boy in a modified version, expanded the register set to 6 8-bit registers for general computation and 3 16-bit registers for indexing and the stack pointer. Then Intel's first stab at the now famous x86 architecture featured even more registers. 8 8-bit registers, which could be combined into 4 16-bit registers, would be used for arithmetic. And 4 additional 16-bit registers are intended for indexing into memory and as a base and stack pointer to track the location of intermediate results in memory. And then jump ahead 30 years to a modern RISC-V architecture, and you have 32 registers at your disposal to store intermediate results, track data across function calls, locate global and thread-specific data, and a lot more. Now, on a more practical note, to add registers to our CPU, we want to organize them in what is generally called a register file. All that really means is that we organize the registers into an array and use write and read ports to move data in and out of the registers. If you recall the register chips that we've used in the processor so far, in the program counter, for example, you'll notice that each chip has its own data input and output ports. So basically, we could just place, say, 10 of these register chips onto a breadboard for 10 registers for our CPU, and then have 10 data input ports and 10 data output ports right there by just hooking up directly to these chips. But those 20 ports result in a lot of unnecessary wires, and we'd be able to write and read all registers at once. In practice, our CPU will only execute one instruction at a time, at least at the beginning. And so each instruction will use up to 2 operands as inputs and produce a single result. So reasonably, we only ever need to read 2 registers at the same time and write a single register at the same time. This is the reason why we tend to organize registers into a register file. We don't need access to all registers in parallel, and it saves a lot of wiring if the register file only provides the minimum number of write and read ports that are necessary to feed the instructions of the processor. The way the write port works is that we can select one of the registers through the write address port and provide the data we want to write at the write data port, which then stores this value in the corresponding register. And similarly, we can select one of the registers for reading through the read address port, which will then present the current value of that register at the read data port. And since we have 2 read ports, we can access the value of 2 registers at the same time. And we can even have both read ports read from the same register, which is just going to produce the same value twice. So let's look at how we can implement this in practice. To actually store the value for each register, we'll simply go with one of the register chips that we've used before in the CPU build, the one that has a clock input and a clock enable input to enable or disable the updating of the stored value. The write data will just wire up to all of the register's data inputs, and we'll use the write address to select which register to enable. There are quite a few ways to do this. For example, by having each register compare whether the write address matches its own address and enable the register if it matches, or by creating a one-hot signal with an address decoder that enables one of the registers based on the presented address. To write something into a register, we simply present the data to be written on the write data port, which transports the data to all the inputs of the registers. And then we present the register address at the write address port, which is going to enable just one of the registers, the one corresponding to the address, and causes it to store the data that we're presenting. And this will work for all the registers. Then to read data back out, we'll add a read data port and connect that to every register through a switch. By closing a switch, we can connect the register to the read data output, which is going to produce the value of that register at the read data output itself. This switch we control like the enable signal of the register, either by having the switch check if the address matches the one of the register, or by using a one-hot signal to close the switch. Reading registers is as easy as selecting a register through the read address port, which is going to close the corresponding switch, which in turn connects the register to the read data output and produces the register's value at the read data output. And since we have 2 read ports, we can do multiple reads in parallel, and we can even read the same register twice. So let's build this up using actual chips on a bunch of breadboards. Let's start out by building a single register of the register file. Going to need a new breadboard for that. Decoupling caps as per usual. The main component of this register is going to be a 74HC377 chip, which is an 8-bit register with a clock enable. Let me also connect the power rails of the breadboard. Let me hook up power and ground of the register. So I think we're going to add one of these bar graph LEDs to show what's currently inside the register. We'll need a resistor array. And a quick check to see if the LEDs are working properly. That appears to be working. Now we'll want to bring the data outputs of the register chip here over to the bar graph LEDs so we can actually display them. And this will be a good opportunity to have all the 8 bits lined up such that we can bring them over to the other chips on the breadboard later on. Okay, that should be all the LEDs hooked up to the outputs of the register here. And then down in the corner here is the clock enable input of the register, which is how we control if the register should store a new value or not. And I think we want to hook that up to an LED so we can actually see that this register is about to update. The LED needs some power. All right, let's see if this works. So down in the bottom left is the clock enable. We'll tie that high, which is the disabled state because it's active low. Up here is the clock input. Tie that low for the time being. And then let me wire up an alternating pattern of 1s and 0s as the data input to the register. Let's fire this up and see if we can store this pattern in the register. Okay, so the register initializes to an arbitrary value. Now the clock is disabled, so toggling the clock should not do anything. And sure enough, nothing happens. But now if I pull the clock enable low, we should be able to clock in the new value into the register. Clock enable LED goes on. And there you go, the new pattern is stored in the register and displayed on the bar graph LED. And let's flip a bit. And if I toggle the clock again, this new pattern appears. And if I change it back, but also disable the clock enable input, we're back to no change happening. Great, so this seems to be working. In order to read out the value of the register, we're going to use a 74HC541 tri-state buffer chip, one for each read port of the register file. And what this allows us to do is select which register should drive its value onto the common read data bus. So let's place them to the right of the bar graph LED. They need power and ground connections. And these buffers have 2 output enable inputs, and basically both have to be low for the output to be enabled and the chip to actually drive a value onto its output. But we only need one of those inputs to actually select a register to drive. So let me connect the other output enable input to ground such that it is constantly enabled. Now let me bring the 8 bits worth of data over from the LEDs to the inputs of the 2 buffer chips here. Now we'll want to be able to see which of these chips in the register file is currently driving a value onto the bus. So what we should do is probably add an LED to the output enable input to see which one is active. Those LEDs need power. Now we'll want a way to look at what the output drivers are producing in terms of data. And in general, we want a way to look at what data goes into the register file and what data comes out of the read ports. So I think what we need is another breadboard on top, which handles the input and output kind of logic and circuitry of the register file. And then we can add bar graph LEDs to that to look at the current state of the read and write data buses. Let me connect the new power rail that we've just added. All right, and then we'll want to add bar graph LEDs over here to look at the data coming out of these chips. And then we can have the bus going vertically through all the chips as they are lined up. We need a bunch of resistors for each of the LEDs. And the LEDs need a connection to ground. Let me quickly test the LEDs if they are working. That looks good. Now for the time being, all we want to do is actually connect these up vertically. So let me do that. What this should now allow us to do is store a value in the register, and then by enabling the outputs of these two chips, we should be able to selectively grab that piece of data and actually put it onto the read bus and make it show up on the LEDs. All right, both are disabled, so nothing shows up on the bus and nothing shows up on the LEDs. But if I enable one of the chips, we can actually see that the data in the register is being transported over and onto the LED corresponding to the read data bus that this chip is hooked up to. And the same goes for the other side. We have a second read data bus for which we can enable the driver and actually get the value of the register being produced on that read data bus. And we can also change the value in the register. And as you can see, the new value immediately shows up at the output. Now I've gone ahead and duplicated this register breadboard. Now let me hook the two up, combine the two power rails, and then let's see how we can actually connect the two registers to form one larger register file. Okay, I think that's all the power connections re-established. Now this second register here has its own set of driver chips here that can actually put the value of the register itself onto the read data buses. So what we need to do is actually connect the outputs of this buffer here to the outputs already up here, and the same over here for the second read data bus. We connect the outputs of this register up to the upper one. And then by selecting one of the chips, we can decide which register to connect to the read data bus and actually have its data appear at the output of the register file. So let's do that. Let's make these connections. All right, so that's the read bus all wired up. Now we have a similar situation on the left-hand side at the actual register chip here, which has its own data inputs, which is basically the way we store data into the register file. And what we want to have at the top, similar to how we have these two read data ports, we want to have a write data port where we can apply data. And the data should be routed to all the data inputs of the registers, and then by picking which of the registers has the clock enabled, we can choose into which register we actually store this value. First, let me make the connections to the top here. All right, so that's the connection to the inputs of the first register here. Now let's bring these inputs down to the second register. All right, so that's all the data inputs wired up. Let's do a similar thing as for the read data ports, and let's add a bar graph LED over here such that we're able to look at what goes into the register file. And now what we should be able to do is wire up the write data input here to a pattern like we had before, maybe alternating ones and zeros, and then store that pattern into one of these registers by selecting the corresponding clock enable input. Speaking of the clock, that's something we also want to hook up. And then let me set up a pattern. And now we need control lines for the write enable inputs and the output enable inputs. And finally the clock. Let's power this up and see what happens. So we see the pattern of alternating bits here at the write data input to the register file, which is what we've configured with these wires here. And then during the power up sequence, because it's kind of like an arbitrary way how these initialize these registers, they already latched this pattern in. But now let's actually change the least significant bit of the input. And now none of the registers is enabled for writing, so toggling the clock should not do anything. Which is correct, nothing happens. But now let's say we want to store this into the first register. So what we do is we enable that register for writing. And then when we toggle the clock, this stores the value into this register. And there you go. And now we can have a different pattern and store this into the second register by enabling that for writing and toggling the clock. And there you go, the value has been stored into the second register. So basically, this allows us to present a value for the register file to store, and then we can pick which register should store the value, and it gets properly latched into it. And the read circuit here on the right allows us to pick which of these registers get to put their data onto the read data outputs of the register file. So say we want to read the first register. All we have to do is pull low the output enable of that register corresponding to that output bus. And we can see the value of the register make an appearance here at the read data output port of the register file. And correspondingly, at the same time, we can decide to also read register 2. And all we have to do is turn on the corresponding output buffer. And the value of register 2 is displayed on the second read data bus. Also note that there's nothing preventing us from reading the same register twice, which just produces the same value twice. And nothing prevents us from reading the registers in arbitrary orders. So now the second register is shown on the first read data bus, and the first register is shown on the second read data bus. So basically the other way around than we had before. Now the big danger and challenge at this point is these output enable lines decide whether a register drives its value onto the read data bus. But it's very easy to create a short circuit like this. For example, what happens if both of these chips have their output enabled? They both would take whatever's at the input and drive it onto the bus. But the first register has the least significant bits set to high, and the second register has them set to low. So there will be a driving conflict on the last two lines here, because this buffer is trying to pull them down to ground, and this buffer is trying to push them up to VDD to represent the 1. And what will happen is basically this buffer here will connect the least significant bits to VDD. This buffer will connect them to ground, and you end up with a short circuit through your system. So what we want is to only ever enable one single driver of this read data bus, and we want a mechanism to select which one of these is responsible for producing an output. To implement this address decoding and pick which of the registers gets to do something, we can use a chip like the 74HC139, which takes a binary value and then produces a range of individual strobe signals with the guarantee that only one of them is ever going to be enabled. So let's do that. And there's some convenient space up here where we can put these chips. Now, since we're adding active logic to the upper breadboard, let me also add a decoupling cap. And then these new chips need power and ground. Now these 139 chips, they have an enable signal, the G input, which allows us to actually say we don't want any of the outputs to be enabled. But for the time being, I think we can tie that low such that the selectors are always enabled. And then maybe we can come up with a fancy use case for them in the future. So each of these chips has 2 decoders, which take 2 input bits and produce 4 output bits. So we have a total of 4 address decoders here. And what we can do now is basically take the outputs of these decoders and wire them up to these output enable and clock enable lines. So let me do that. So I'm going to leave output 0 unconnected such that we can apply register address 0 and basically have that mean that we would want to read none of the registers, or we want to write to none of the registers. And the same for the clock enables over here. And now, instead of fiddling with these individual strobe wires, where we have this constraint that only one of them ever can be active, we have a much more convenient input here of 2 bits for a 2-bit binary number, which picks which one of the 4 outputs is active. So let's wire this up. So I've connected the 3 register address inputs here to all zeros. So these should select register 0, which doesn't exist, for reading and for writing. And so in essence, none of the registers should actually be selected to do something. Let's give this a try. All right, so this brings us up in some random state, which happens to reflect what was stored in the registers before. And now we should be able to use these 2-bit register addresses here to select which of the registers should do something. So this here is read address 2, which corresponds to the read data bus 2. Currently this is at 0, but if I increase this to 1, you can see that we actually select register 1 for outputting on this read data bus, and we can see the value of register 1 appear here. And similarly, we can pick address 2, which is the second register. And as you can see, the output enable goes high for this driver buffer here and produces the value of register 2 up here at the read data port. And similarly for the address 1 here, we can pick, for example, 1 for the read address 1, which is going to produce the value of the first register on the first read data bus. Or we can change this to 2, which then effectively reads out the second register through this read port of the register file. And in terms of writing, none of the registers is currently selected because we're applying write address 0 here, which is basically saying don't do anything. Well, let me change the pattern a bit. And now toggling the clock doesn't do anything. But if we select register 1 for writing, you can see that the write enable of the first register goes high. And when I toggle the clock, the new value gets latched in. And if we change the value again and select a different register, register 2, we can store this new data item into register 2. And since we're also reading register 2, we can immediately see the new value make an appearance at the output of the register file. All right, so I think with this, the first version of the register file is all complete. We have 2 registers, we have 1 write port and 2 read ports, and we have a corresponding write address input and write data input to perform writes into the register file. And we have 2 read addresses, with correspondingly to read data buses here that can actually read data out of the register file. And by picking these addresses here, we can choose which register we write and which register we read out. And as you can imagine, we could just keep going and replicating registers and just add them to the stack. And as long as we find chips that can convert binary numbers into these one-hot encoded signals to produce the output enable signals, we can have very convenient addresses here that we can change in order to select which of the large stack of registers should actually be read out or which of the registers should be written to. But for the time being, I think just 2 registers is quite enough, and we can use that to get started with some of the instruction encoding business, which is also super interesting. And then in the future, what we probably are going to do is we're going to turn these registers into a PCB because the pattern is pretty repetitive and it has a lot of wiring. And then we'll have 4 of these PCBs arranged in a stack such that we can have 4 actual registers to work with. And I'm pretty sure we'll expand that as the CPU keeps growing and we expand also the functionality. Especially I have a suspicion that we want 3 read ports because we're dealing with a 16-bit system. So for certain things like jumping to an address stored in a register, it would be useful to read 2 8-bit data items at the same time in order to get a 16-bit value to jump to. But this is for the future. We'll see how that plays out. All right, in the next episode, I think it's time to integrate this with the other half of the CPU that we've built, which is basically the program counter and the program memory. And we can hook these control wires here up to parts of the instruction and actually do something useful with the register file already. Thanks a lot for watching. Like and subscribe if you want to see more of this, and see you again next time.